Today is lecture 5 of physical metallurgy. Happens to be 5th of September 2017. So today we'll continue with the iron carbon diagram, steel metallurgy. Because steel metallurgy basically covers a lot of physical metallurgy. So when we study steel metallurgy, we study many aspects of physical metallurgy. So let me recap what we have done last week. So I'm going to draw the iron carbon diagram again, and just as a recap. So in the iron carbon diagram, we have, as always, temperature on the vertical axis and percent carbon on the horizontal axis. This is weight percent, always. So in metallurgy, we always use weight percent. Okay, so the first reaction when you cool the metal from the molten state is what we called the peritectic reaction. So this is peritectic reaction. Now, iron melts at 1538 C, and this peritectic reaction is at 1495 C. And this composition here is about 0.53% carbon. Now, this reaction is not important for us because when the metal cools down from the liquid state to the solid state, this is gamma. This is also called austenite. And so whatever happens in this regime, it doesn't affect the austenite. And so we really are not concerned about this reaction here. So if I take this liquidus down here, I bring it down here, there is a eutectic reaction over here. And this happens at 1148 C, and this composition is 4.3% carbon. And this is a eutectic reaction. And this reaction is also not important for us because this is about 2% carbon, and steel is in this region. So we're dealing with steel. This portion is cast iron up beyond 2% carbon. So we're not dealing with cast iron right now. So the reaction of interest to us is this eutectoid reaction, which this is the eutectoid reaction, EUTECTOID. And this happens at a composition of 0.77% carbon, and the eutectoid temperature is 727 degrees C, and this temperature here is 912 C. And this composition is about 0.02. And if I extend these lines, we go to 6.7% carbon, and this is Fe3C. We also call it cementite. And here we have, okay, this is gamma. So this is gamma plus delta. Delta is ferrite. And this space, so this is delta, which is ferrite. So this is delta plus Fe3C. So this is the iron carbon diagram we looked at last time. So we have three reactions: peritectic reaction, eutectic reaction, and eutectoid. So for steel, we're basically interested in this region over here, and we can forget about the rest of the diagram. So the first question comes up: what is austenitite? So austenitite, AUSTENIT. So austenitite is, we call the gamma phase also. So this is the structure of austenitide is face-centered cubic. So face-centered cubic is the structure. The unit cell looks like this. So question is, what is the unit cell? So unit cell is the so this is a unit cell. So unit cell is the minimum structure that defines the overall extended structure. So this is the minimum, has the minimum, let's say, structure that is needed to define the overall structure, right? So this face-centered cubic structure basically has atoms at these cubic corners. So the 8 of them, I'll just draw the 5. And then we have face-centered cubic. So each face has an atom. So this is the FCC, face-centered cubic structure. So this structure is important because it's the most dense structure you can have, most dense structure possible. You can't make atomic structure more dense than this. So if I take a plane, so I'm trying to draw something in 3D. So if I remove this atom and I draw a plane that looks like this. So I'm drawing a plane like this. If I were to, so let me draw the plane. So that plane will have atoms that'll be like this. So we call this close packed. So this is like hexagonal structure. So all these atoms, so what do I mean by hexagonal? If you look at this like this, you have a hexagonal structure, right? So all these atoms are touching each other. So on this, if I look at this plane, it's got 3 close packed directions. So close packed directions. So one is this, one is this, and one is this, right? And if you look at this, I've drawn one plane. Just like this, there are 4 planes of this type in the structure. And each plane has 3 close packed directions. So basically the message here is any direction you look in, this is a very tight packed structure. So why is this important? The reason this structure is important, because as we go along we learn that the face-centered cubic structure, the FCC structure, is critical to well-being. Without this we can't have civilization, because this makes these metals have very high ductility, meaning we can work them to very high deformation. So we can work them to very high degree of deformation. So if you know that, so aluminum foil. Now aluminum foil is made, you start off with a huge ingot, probably 1 ton, huge chunk of metal, and you roll it into like a mill thick piece of metal. So obviously aluminum has to be FCC structure, right? For such extreme ability to be deformed. What about gold? Gold also can be deformed into very, very thin foils. So if you go to India and you buy candy, some of it comes gold wrapped. So and this penny costs pennies, this candy costs pennies, right? So the gold can be beaten with a hammer to extremely thin thickness that it becomes basically so cheap, right? What about copper? Copper also can be beaten to whatever extent you want, it won't break. So copper is very ductile. Silver. So silver is also FCC's face-centered cubic structure. Great. So gamma, our austenitide, is face-centered, has face-centered structure. What about our delta? Delta is our ferrite. A delta ferrite, that is not FCC, that's a BCC structure. So BCC stands for body centered cubic. Now BCC structure is, again, let's draw the unit cell of the BCC structure. So here's a unit cell, and we have Fe atoms on each corner of the unit cell. So these are all Fe. And we have body-centered cubic. So in the middle of this belly of this cell, there is another iron atom. So this is body-centered structure. Now this is not as dense. So this would be less ductile. It's still ductile, less ductile than the austenitide structure. So in our iron carbon diagram, we see at room temperature we have delta, which is not as ductile, and we have Fe3C, which is intermetallic, it's brittle. So that's where we end up. Now there's another very important alloy, which is FCC, and that is 300 series stainless steel. So we use a lot of stainless steel, 300 series. So this is austenitic stainless steel, and this is also FCC structure. So basically what we do is, so notice this austenitide region is, let me just draw the boundaries of austenitide region. This is this region. So this exists above 727 degrees centigrade in the iron carbon steel, but when you add nickel to this, you can bring this down to room temperature. So the austenite can be stable at room temperature. So when we study stainless steels, we'll understand how 300 series becomes austenitic stainless steel. So the way I plan to teach this course is, rather than have a whole chapter on structures which gets boring, I will keep introducing some fundamental ideas as we go along. So this is a minor deviation from a lecture on steel, because I just want to introduce a little bit of the crystal structure of the austenitide and the ferrite. Okay, so today we want to study the pearlite transformation. P-E-A-R-L-I-T-E transformation. And this is probably the most important transformation in steel, and it basically centers around this pearlite composition. So when you say pearlite, we mean a steel that contains 0.77% carbon. So this is the pearlite composition. And we want to study how the steel performs as we cool this pearlite composition. So we'll start with this pearlite composition. So in manufacturing, whenever we do manufacturing, processing of steel, we can do one big step is annealing. We can anneal the steel. So annealing means cooling in the furnace. So what we do is, if we have this pearlite composition, we would heat the steel into the austenitide region, let's say 800 degrees centigrade. So cooling in the furnace from, let's say, 800 degrees centigrade. So we heat the steel to 800 C, we hold it there for an hour or two, and then we turn the furnace off and come back next day, and the steel is cold. So cooling in the furnace. There's another way we cool, and that's called normalizing. So normalizing means cooling in air. So we would heat the steel to, again, let's say 800 degrees centigrade, which would be in the austenitide region, and from there we would cool in air. So this cools much faster. So whatever way we cool, so the cooling affects the structure of the steel. So when we are doing our introductory lectures on steel metallurgy, depending on how we cool, we'll get different crystal structure. So, and that's kind of confusing. So the first step we want to do is to do isothermal transformation, meaning, okay, so let me go slowly to this side over here. And so we want to cool the steel very slowly. So we get a structure we would call, so it's the structure is based on the phase diagram. So the phase diagram is for reversible reactions. So this is done with very, very slow cooling. So since we're studying phase diagram and the structures that result, we want to do isothermal transformation. So isothermal transformation. And once we do the isothermal transformation, understand isothermal transformation, we can take this information and understand what happens during normalizing, during annealing. So what do I mean by isothermal transformation? So let me redraw the iron-carbon diagram that's of interest to us today. I'll only draw the eutectoid reaction. So we're dealing with the eutectoid reaction. So for that, we have the diagram that looks like this. This composition is 0.77% carbon. This temperature is 727 C. This is 0.02% carbon. And this temperature is 912 C. Let's see, what else is there? Okay, so this is austenitide. This is delta plus austenitide plus delta plus Fe3C. And the Fe3C is here. This is Fe3C at 6.7% carbon. So this is our phase diagram. So what we want to do is to take this eutectoid composition, heat the steel to this temperature just above the eutectoid and then cool it to temperature just below the eutectoid or to any other temperature. So how would we do this? So I would like to heat the steel to within the austenitide region and then cool it to whatever temperature I want and hold it isothermally at these temperatures. So for that, what we would do is to take a furnace, we take a furnace and we have a salt bath in it. So this is salt bath, this is salt, it's molten salt, and this furnace is, let's say, above 727 C. Then I take another furnace which I hold at some temperature which is below 727 C, and again I have a salt bath in there, molten salt. And the third one would be just water for quenching. So what I would do is to take a piece of small piece of steel as big as a dime, maybe attach a wire to it, and put the steel in the salt bath. So we let it stabilize in this temperature above the eutectic for, let's say, half an hour. Then I take this steel and I put it here, so which would be a temperature below the eutectoid for whatever time you want. You decide 10, 15, 20 minutes, 5 seconds, 10 seconds, and then you transfer it over here into the water. So when the steel is here, the structure is austenite. Austenite. I'm saying austenitite is austenite. So structure is austenite over here, and over here it's some delta plus Fe3C structure, which is perlite. And we'll discuss what perlite is. And then we quench it. And from here to here, the structure doesn't change because we just quenched it. So the idea is we want to study phase transformation under very slow cooling conditions. So whatever happens to the structure is the same as what the phase diagram predicts, So this is isothermal cooling, and so let's see, when we cool to this point, how much delta do we have and how much Fe3C we have. So for that, we apply the lever rule, LEVER rule. So the percent delta in this, so this is eutectoid composition. So how much delta do we have? The amount of delta would be, by the lever rule, it would be 6.7% minus 0.77%. That's this length divided by the total length, which is 6.7 minus 0.02. This comes out to be about 12%. No, 88%. And then the fraction, the percent Fe3C, by the way, this is all weight percent, would be this divided by the total. So this is 0.77 minus 0.02 over 6.7 minus 0.02, and that's 12%. So this is 6.7. So now the density of ferrite and Fe3C is about the same. So the volume fraction of delta would be 88%, and the volume fraction of Fe3C is equal to 12%. So what does the perlite look like? So perlite structure looks like bands, lamellae of Fe3C. So I've drawn this dark line is Fe3C, and the space in between is alpha. So the width of this line, the thickness of this line is, let's say, T Fe3C, that's the thickness of the line, and this is thickness of alpha, T of alpha, this would be like 1/7. So the space between these lamellae is 7 times more than the thickness of this ferrite. So you basically have these platelets of Fe3C. These are plates. I've taken a cross section. So these are plates of Fe3C in a matrix of alpha, and the thickness of these Fe3C plates is 1/7 the thickness of the alpha in between. So this is the perlitic structure. And so let's talk about the cooling from here to there. And so let's just discuss how does the perlite structure form. So when we are so in the austenite region, which is above 727 degrees C, if you were to be able to look at the crystal structure, which of course you cannot, you will see what we call like equiaxed structure. So equiaxed. So this is a very common term in metallurgy, equiaxed. So what that means is the grains have no preference in terms of shape. For example, a structure where the grains look like this is not equiaxed. So these are elongated grains, right? So when the grains have the same shape in any direction, then it's equiaxed. So this is not equiaxed. So when we heat steel up into the austenite region, the delta ferrite and the Fe3C, they combine into one phase that's austenite. And that's the FCC structure that we discussed, right? So you have homogeneous austenite. Austenite is homogeneous, which means that's the only phase there is. There's no Fe3C over here, no delta over here. So now we cool the structure below the eutectoid. So what will happen is that the Fe3C and so basically the perlite will come out. So perlite will grow only in one side. So if this is austenite gamma 1, this is austenite gamma 2, two different grains, the perlite will only grow in one side of into one grain, it won't grow in the other grain. So over here, the perlite might grow like this, over here it might grow like this, over here like this. So it's only going to grow into one grain. It doesn't consume, like it won't consume both the grains as it grows. It'll only consume one grain. So it'll take the path of least resistance, it'll grow into one grain. And so this is something that we learned only recently, as research done has shown this. And what happens when the perlite grows like this, if I draw it a little big, let me just draw an expanded view. So we have gamma 1, gamma 2. So these are two grains like gamma 1, gamma 2 of austenite. The way the pearlite grows, let's say, into gamma 2, so you'll have these lamellae of Fe3C growing like this, and they have a certain crystal structure and orientation, right? And so does the delta, the ferrite. So these orientations will be in relation to gamma 1. So gamma 1 has a certain orientation, crystal orientation. The Fe3C and the delta will have a relationship with gamma 1. So even though they're growing into gamma 2, the crystal orientation relationship is with gamma 1. So that's something we have learned recently, you know. Okay, so with that note, let me just spend a little bit more time on how the ferrite grows. Now, we don't have a full understanding of, one other thing is, when the pearlite grows, it grows like in every direction. So it tries to grow in not just one direction, it grows in every direction. So how does how does pearlite grow? So think about, let's say this is gamma 1, this is gamma 2, 2 grains of austenite. Now suppose you have grown one plate of Fe3C. So this is like a plate in this direction. So I can just draw it dark over here. So as this plate grows, it becomes thicker. So what happens is, okay, so this is this gamma on both sides, gamma 2. So the carbon composition drops. So the carbon composition over here is, let's say, 0.77% carbon, right? And so carbon composition is like this. So since Fe3C is consuming the carbon, so carbon composition drops. And because of that, when this drops to, let's say, 0.02%, then the ferrite begins to grow. So now ferrite is growing, and when ferrite grows, the carbon composition goes up because the ferrite is just Fe, so it doesn't need so it rejects the carbon. So ferrite is growing, and this carbon composition is going up. And then when it gets to 6.7%, then the Fe3C starts growing. So this happens on both sides. I've only drawn one side. So just imagine this ferrite on this side, and then again you have Fe3C. So it alternates. So basically, we call this sympathetic sideways growth. So assume Fe3C forms first, it consumes the carbon, so the carbon content goes down, so then the ferrite grows. As a result of ferrite, the carbon concentration goes up, so then Fe3C grows, and so on. So this explains the lateral growth of the structure. But you also have to grow in that direction. So don't ask me how the growth happens in that direction. But the growth happens in both directions. Okay, so let's talk more about the growth of pearlite. So we're talking about the growth of, so what are the kinetics of pearlite growth? So growth of perlite. So as I mentioned, it grows in every direction. And it'll keep growing. It'll keep growing until it hits a boundary, then it stops. So it can grow to a certain extent. But while it's growing, if I plot the size of perlite colony, so think about this thing as a perlite colony. So it's growing. So if we draw the size of that colony versus time, it's linear. So the growth rate is constant. So let's recap a little bit. What we have done is we have heated the steel into the austenite region. So let's say we heated the steel to 800 C in a salt bath, and then we put it in another salt bath to, let's say, this temperature. And let's say by magic, we're observing how the perlite is growing at that temperature. It'll have this growth rate. So let's call this T1. So at temperature T1, it'll grow like so. At temperature T2, it might have a different growth rate, temperature T3, but they're all constant. And so they're functional temperature, but not time. So what is the effect of temperature on the growth rate? So let's discuss the effect of temperature. So effect of temperature on growth rate of perlite. So what we have done is we have heated the steel to 800 C, we have quenched it to some temperature over here, and we're studying how fast does the perlite grow at these different temperatures, and the plot would look like this. So this is the growth rate. So this would be in millimeters per second, right? And the vertical axis is temperature. So the highest temperature we have is 727 degrees C, right? So because below that, you have the perlite growing. So growth rate would look like this. So there is a maxima. So as you cool the steel, the growth rate will as you keep it. So this is isothermal transformation. So we're keeping the steel fixed at a certain temperature at these different temperatures. So you get, let's say you take readings at different temperatures. You get a curve like this. So at each temperature, the growth rate is constant, but the growth rate is a function of temperature. So that's important. Now, so this is growth rate, but you also have nucleation rate. So if I can go over here, so nucleation rate. So suppose you have your austenite, which looks like this. So this is your gamma, your austenite. Now, at some temperature, you might get perlite forming over here. You might get perlite forming over here. You get perlite forming over here. So growth rate is measured in terms of number of nuclei formed per unit volume per unit time. So how many nuclei formed in a unit volume per second? So that's nucleation rate. So if you have many nuclei forming, that's high nucleation rate. If you have only one or two, that's slow nucleation rate. So if I were to plot nucleation rate on the same axis, it would look like this. So this is nucleation rate. And the black one is growth rate. So perlite will first nucleate and then it'll grow. So first the nuclei will form and then they'll grow. So all the nuclei will grow. So the question is, how many nuclei form per unit volume per second, and how do they grow? So the black line tells you, as a function of temperature, what is the growth rate, and the red line tells you at what rate will they nucleate. So notice there's a gap over here. So at this temperature, the growth rate is fast, but the nucleation rate is very small. So nucleation rate is very small. So as you decrease the temperature, the nucleation rate increases, and so does the growth rate. But the growth rate in this temperature region is faster than the nucleation rate. So this is important because we want to talk about what happens to steel when we cool it. So for that, I'm going to draw what I call a cooling curve. Let's see, what do we call the cooling curve? So it's isothermal. So isothermal cooling. So basically, I'm plotting time temperature curve. So there is temperature on the vertical axis and time on the horizontal axis. And so so here our maximum temperature would be 727 degrees C. So we do our experiment where we heat the steel to, let's say, 800 degrees centigrade, and let's say I cool it to, for our experiment, let's cool it to 700 degrees centigrade. So we take a steel at 800 C, we cool it to 700, and then we hold it at 700, and we see what happens. What will happen at 700 is that the perlite wants to grow fast, but there are very few nuclei. So I'm holding the steel at 700, and I'm waiting for the perlite to form. I'm waiting, and the perlite starts forming over here. So at this point, I have 1% of the structure is perlite, and the rest is austenite, right? It's because at 800 C, it is all gamma. It is all austenite. So 800 C, it is all austenite, and I cooled it to 700, and I'm holding it there. I start over here at 0 time, right? So this is 0 time. I start here. So I cool the steel to 700. Then I'm waiting. At this time, I get 1% perlite. And then I keep waiting. At this temperature, at this time, I get 99% perlite. So let me recap. What I did was, if you look at this phase diagram, I heated the steel to 800 C, and I cooled it quickly to 700. And I'm looking at the structure because I'm a magician. At 800, at austenite, and at 700, I'm looking at the structure, and slowly, when I get to this time over here, I see 1% of the structure is perlite. And then at this time, it's 99% perlite. So I note down these 2 points. So then I do another experiment. This time I start at 800, so let's call this 800C. So I heat the steel to 800C, then I cool it to 600. At time 0, I have no perlite. I wait. And at this point, I get 1% perlite. Then I wait. At this time, I get 99% perlite. And then let me do 550 degrees centigrade. I heat to 800, I cool. At this time, I get 1% perlite. Now I get 99%. So I can take these curves, points, I can join them. I get this kind of region. So notice that here I have gamma, over here I have gamma plus perlite, and over here I have perlite. So what have I done? I have temperature time axis. I'm doing isothermal transformations at different temperatures. I hold the steel at 700, see when I get 1% perlite, when I get 99% perlite. I hold another piece of steel at 600, perlite starts forming over here, completion over there, and so on. So this is time temperature diagram, isothermal for perlite formation. So reason we're doing isothermal transformation is because we can do it. If we were to cool continuously, we cannot draw these diagrams, So what happens below this? Let's suppose, what happens below 500 degrees centigrade? Okay, so up to this point, we know what gamma is. Gamma is austenite, and we know what perlite is. Perlite is delta ferrite plus, let's see, plus Fe3C. So we know what gamma austenite is. We know perlite is a combination of delta plus Fe3C. And the structure of perlite is lamellase of Fe3C. So it would look like this. So this is perlite. So clearly in perlite, you have alpha matrix. No, not alpha, delta matrix, which is ferrite, plus you have Fe3C lamellae. So lamellae of plates, lamellase of Fe3C, plates of Fe3C in delta, which is also ferrite. So that's perlite, right? This is perlite. So we have seen how we have isothermal transformation of austenite into perlite. Now something strange happens when you do the same kind of test experiment at lower temperatures. Now what happens is the curve bends like this, and you don't have perlite anymore. So we know this is gamma. So instead of perlite, you get gamma, plus you get bainite, and then this is bainite. So what is bainite? Bainite. So bainite is also alpha plus Fe3C, or it can also be alpha plus carbide. So Fe3C has a different structure from carbide. This is also Fe3C, but it's a little different composition. Fe3C, we know, is 6.7% carbon, right? This carbide is about 8.8% carbon. So this is also iron plus carbon, but different composition. But this structure is very complicated. And it's not like this. It's basically a dispersion of carbide I keep saying alpha, this is delta. So so this bainite is particles of carbide or Fe3C in the ferrite, but it's very, very fine dispersion. It's not neat looking as the pearlite structure. For example, you can cross-section the pearlite, you can measure the thickness of these plates, and actually you can tell, so you can tell at what isothermal temperature you cool the steel, because the thickness of the Fe3C is also a function of temperature. So from the structure of ferrite, you can actually tell at what temperature you did the transformation. But the bainite is a very complicated structure, very hard to analyze, and we really don't have enough understanding of bainite. So what if, there's another temperature which is called MS. So M stands for martensite. Well, let me write it over here. So M stands for martensite. So martensite is a very important phase in steel, and it happens. So if I were to take the steel at 800 degrees centigrade and I cool it to below the MS temperature and then I hold it, it'll become martensite. And that is a very hard material. So martensite hardness, HRC, can be, let's say, 67, which is like your knife at home, kitchen knife in a fully hardened condition has Rockwell C hardness of 67. So just to recap, what we've done here is if I take steel at 800 C, I cool it to this temperature, then I hold it at that temperature. At this point, pearlite will start forming. At this point, the transformation is complete. If I take that same steel, I start at 800, quickly quench it to this temperature and hold it there. At this temperature, I get bainite. At this time I get bainite. At this time, bainite transformation is complete. Then I have all bainite. Now, if I take the same steel and I cool it down to this temperature, hold it there for time, I get martensite. So those are the three structures you can get with this isothermal transformation. So pearlite is the softest, bainite is harder, and martensite is the hardest. So with that, I'm going to stop today, and next time we'll do more on this diagram. By the way, I forgot to mention, this diagram is called TTT curve. TTT curve. So that stands for temperature, time, transformation. So what we have done today is we have taken a simple approach of isothermal transformation, meaning holding the steel at a fixed temperature. But in manufacturing, we don't do this. In manufacturing, we do continuous cooling. We cool like this, we cool like that, we cool like so. So hopefully in the next class, we'll discuss continuous cooling of steel and what happens. So any questions? Maybe I can open up the phone line. How do I open up the phone line? What do I do? Do I unmute? No, it's unmuted, right? The green is on. Any questions? Okay, we'll call it a day. Thank you, guys.